All right, so chapter 15 is broken into two sections. First section is based on IR. We've already seen a lot of IR in lab, right? Most of you, based on your lab reports, are fairly comfortable interpreting IR spectra. However, I know some people are a little rusty, and so what I've done is I've gone through and created a supplemental video lecture that's posted on the class website. So if you do want to go back and review IR material, pull up that video. You can hear my cats fighting in the background. It's a good time. And I've got notes in the class notebook that kind of explain the premise of spectroscopy, where we talk about using different frequencies of electromagnetic radiation for different sorts of spectroscopy. I walk you through concepts behind IR, tips for interpreting IR spectra, and then I even walk through some practice problems from the book. So really good review if you're rusty on IR, but I'm not going to spend a lot of class time on it because mass spec, in my opinion, is the trickier, newer concept that we haven't seen before. So let's talk about mass spec. Does anybody know what mass spec does? Daniel? Do you know what mass spec does? So you can use mass spec to identify chemical compounds, and what primarily are we looking at when we're identifying them? The mass. So you can look at the mass. What other features can you maybe see in a mass spec? Yeah, you can see ratios of peaks. My analogy for mass spec is it's like going into a war zone, looking at a shattered building and trying to figure out what the building looked like before you blew it up. You can determine a lot about a molecule by the pieces that you break it up into, right? So mass spec is really a destructive technique, but a useful technique for figuring out what your original unknown molecule looked like. So let's kind of look at an example of what's going on in a mass spec. And I'm just going to choose a generic carbon-carbon bond here. And what we do is we inject this into a mass spectrometer, and the mass spectrometer will actually slam this with electrons. So it will shoot electrons at our molecule, and it almost becomes like a game of billiards, right? We've got electrons in our sigma bond, and if we fire an electron beam at sigma bonds, we can dislodge an electron that's maybe located in this sigma bond. So if we look at this, if we knock one of these electrons out, we now have an unpaired electron between two carbons. And if we lost an electron, meaning it got knocked out by that electron beam, is this now an anion or a cation? Yeah, it's only one electron where that sigma bond used to be. It's a cation. So we just lost an electron because it got knocked out by that electron beam, so we've essentially turned our parent molecule into a cation. And this is really useful for mass spec, right? So we've done this, and we've knocked out an electron. Mass specs primarily look at cations. They don't look at neutral molecules. They only look at cations or anions. Specifically, what we call this is a radical cation. If you remember back to, I think it was chapter 11, radicals are any organic molecule with an unpaired electron. Because we knocked out one of those electrons, this is both a radical and a cation. These are highly, highly unstable. What ends up happening is that they will fragment further inside the mass spec. So what we can do is we can have this electron just hop over to one side of our radical cation. Now when we do this, we end up with a cation on one side and then a radical on the other side. So let's label these. We've got a cation. We've got a radical. If you remember, I mentioned before that mass specs can only see cations. So let's even circle these and we'll say mass spec can only see anions. you can't observe the radical because they are uncharged at this point. All right, so let's kind of investigate why mass specs can see cations or anions. And let's imagine that we're a cation. Do some role playing. Here I am. I'm a cation. I'm flying in that direction. And all of a sudden, I fly past this dipole or this magnetic field where I've got a north pole and I've got a south pole. What do you think will happen if I fly through this magnet? I'm going to bend down, right? So opposite charges attract, like charges repel. So if I look at this, I could say, well, if I went straight, I'd be going along this dotted line, but likely I'm going to end up being deflected downwards due to this magnetic field. When I do this, I'll eventually run into a detector. And this detector, what it does is it essentially measures the amount of deflection that's occurred. So in this case, I was deflected down by the amount shown by that red arrow. And this tells me a lot. It tells me, first of all, well, we can deduce the mass. It tells us a lot about the charge, right? So if I had, let's say, a +1 charge, I'd get deflected a certain distance. If I had a +2 charge, I'd get deflected even more, right? Because that +2 charge would interact more with the magnet. And it can tell us a lot about the mass of the molecules. So light molecules will get deflected a lot more than heavy molecules. So let's take a look at this. My cartoon's not the most elegant picture of what a mass spec actually looks like. So I pulled this one from the book. Let's blow it up a little bit. And you can see clearly that on the inlet where it says sample molecules enter here, you essentially inject in a microgram quantity of your sample. It goes into this heater, which will vaporize your molecule into the gas phase. Then we slam it with an electron beam. That's what knocks out one of those electrons. It forms your radical cation. And then it gets accelerated through a series of electromagnets into an ionizing chamber. And then you can see that north and south pole magnet. That's what deflects our radical cations, or our cations in general, into a detector assembly on the opposite side. The mass specs that are currently used today can be infinitely more complicated than these. This is the most basic mass spec diagram I could find. If you go into a research lab, some modern mass specs cost upwards of $1 million, and they can tell you to a part per billion level what the mass is of a sample. So for example, some modern mass specs will tell you accurately the molecular weight of a protein, of an RNA, of a DNA strand. They're getting really, really good at making highly sensitive mass specs. So let's just use this simple example, and let's take a look at what mass spec data actually looks like after the computer spits it out. And let's say I inject methane into my mass spec. If you look at the bottom, it has something called the M/V. M/Z is equal to your mass to charge ratio. Not ration, ratio. So in this case, our mass to charge ratio is usually a charge of 1. So what we're seeing most of the times is just a scale with mass on that bottom axis. It's not accurate if you have more than one charge in your molecule. So if you've got 2 cationic regions, it won't accurately tell you the mass. It'll instead be a half mass. But usually it's 1, so we'll stick with that as a general assumption. Usually the charge is 1, so M to Z equals mass. All right, so let's take a look at that spectrum again. We've got methane. Methane, carbon has an atomic mass of about 12. We've got 4 hydrogens, so we just do some simple math. 12 plus 4 we would anticipate that the mass of methane should be 16. All right? So if we go over and we look at this, we could say, all right, 16 is right there. That corresponds to this peak. What the heck are all the other peaks? What do you guys think? It could be some hydrogens that got dislodged. So like I mentioned, mass specs obliterate your molecules. So these lighter portions down here, specifically lighter than down here, these could be fragments, meaning they're the pieces that got obliterated in the mass spec. What about that little peak that's one above that? Isotopes, right? We're taught that carbon always weighs 12. Not the full story, right? There's some isotopes of carbon that are a little bit heavier. So if you've ever heard about carbon dating, what does carbon dating look at? Carbon 14. So we have the most abundant isotope of carbon, that's carbon 12, but we also have a little bit of carbon 13 and even a trace amount of carbon 14 in our environment. So mass specs will even pick up isotopic abundance of different elements as they fly through your mass spec. So in this one, you can clearly see that we've got a sample with a little bit of carbon 13 down there, and it's super tiny because carbon 13 only makes up about 1% of all carbon on our planet. It's not very abundant, but you can see it very clearly on mass spec, and it becomes a useful tool, which I'll show you guys later. All right, so let's discuss terminology a little bit. The big peak that we see here is scaled to 100%. Oftentimes that's called the base peak or just the biggest peak. And the peak that's furthest to the right and biggest is called our parent peak or our molecular ion. And people will oftentimes abbreviate this as M cation radical, so plus dot. That's just our parent radical cation where we dislodged one electron. And then down here, we've got mass plus 1 radical cation, and we said that that is due to our heavier isotope of carbon. And everything below that are fragments that are all cationic fragments, probably due to loss of a hydrogen. Okay, so let's take a look. Yep.
What section is this, chapter 15?
Yes, it's chapter 15. Section 1 through, I can't remember how many sections is on IR, but we're kind of glossing over that because we've already used IR considerably in lab. So this starts kind of midway through chapter 15. Yep.
What's the parent?
So the parent peak is the one furthest to the right that's biggest, right? So if we look at this, it's furthest to the right and it's largest.
Oh, so base peak and parent are the same thing?
In this case, it is. I'm going to show you guys some more complicated examples, and we'll kind of discuss it in more detail, though. All right, so let's take a look at another useful aspect of mass spec, and that's that parent peak that I was talking about, the one that I said was on the far right. We said the parent peak was right here. That's just essentially telling us the mass of our molecule, right? So we said the mass of methane should be 16. So this approximately correlates to this parent peak or our base peak in this case. If we look at a more complicated molecule, that's when things start getting a little bit more tricky. So what molecule is this? Please tell me you guys can name this. Pentane. N-pentane specifically. All right, so if we look at N-pentane, what should the molecular weight of N-pentane be? We can do the math, right? So we've got C5, we've got 3, 6, 7, 8, 9, 10, 11, 12, H12. So that's 5 times 12 is 70, plus 12. Wait, am I doing this wrong? 60. This is why I don't teach math. 72, right? So we'd anticipate the molecular weight of pentane should be 72. If we look at our mass spec, we've got a peak right here at 72, right? If we look at it, this is our parent peak. It's not very big, but it's the one furthest to the right. So it's the rightmost cluster, and it's the biggest cluster within that subgrouping, right? So if we look at this, we would label this as our parent radical cation. That's the one that tells us our molecular weight. Yep.
Where did you get 60 and 12 again?
So for carbon, our carbons, we've got 5 of them. Carbon weighs 12. So that's 60 total for our carbons and then 12 for hydrogens. That was just our back of the envelope calculation for what our parent peak should be at. All right, so now the question is, what the heck are the rest of these peaks? It's other carbons. Let's do a little bit of a trick. Well, not a trick. We'll do some work. Oh, work. Like we just had an exam. Why are you doing this to us? Just leave me alone. All right, so this one on the far right still has all of our carbons and all of our hydrogens. We've just knocked out an electron. What do you think this one is over here? What do you think we maybe lost? Electrons weigh a lot more than an atomic mass unit. A methyl group. So let's just say, all right, what if we lopped off this methyl group coming off that right end, and now we've got a butane fragment. How much should a butane fragment weigh? We can do our quick calculation. We've got C4, we've got 3, 6, 7, 8, 9, 10. There's, all right, yeah, 6 plus 4 is 10, roughly. Oh, man, age 10. This is what happens when I wake up at 3 in the morning. So 4 times 12 be 48 plus 10. We should have a peak at roughly 58 for this butane fragment. So if we look at this peak, we can say, oh, there we go. We've got 55, 56, 57. That's pretty close. The reason we don't have 58 is because we really don't have 3 carbons. If we look here, we only have 2 carbons and then a cation, right? So we could go through, fill in all these hydrogens. And this could theoretically be just a butane fragment from our original ion, right? What do you think these pieces are at the slightly lower level? Yeah, hydrogens being popped off. So we could knock off individual hydrogens off of that butane fragment, and we could see those too. However, the biggest peak usually corresponds to the most predominant fragment in the sample. All right, so now let's take a look at this next one. What do you think that biggest peak around 40 is going to be? Yeah, a propane cation. So if we do this, it could just be another carbon getting lopped off. And then as we go down, we could say, all right, this could be an ethane cation. And then the last one, could just be our methane cation. All right, so anytime we see a mass spec, we typically see all of our various fragments. Yep?
Does base peak and parent peak the same thing? Or?
No. And let's talk about that briefly. This peak over here, we call our molecular ion, often referred to as our parent peak because it tells us about our original molecule. Our base peak is just simply our biggest peak in the spectrum. So if we look at our base peak, it would be right here. So if you look at our scale on the left, that's our relative abundance. Our relative abundance is always scaled to our biggest peak, meaning our base peak. So this base peak was scaled to 100, which means if we look at this, we could say we have approximately 10% relative abundance of our molecular ion compared to our most abundant ion in our mass spec sample. Yep.
So if this was like one methyl instead of, I don't know, if you have the same number of carbons but a different structure, would these still be the same?
Not exactly. We'll go through more examples, but what I always imagine is taking out my molecular scissors and cutting every single bond and trying to form the most stable cations. We'll take a look at this later, but right now we're just looking at relatively simple examples. Did you have a question, Chloe? Yeah, we're kind of scratching the surface right now, but we're going to get into identifying functional groups and branching probably tomorrow when we get there. Were there more questions?
I just have a question for like the 30 mark for the ethylene carbon cation.
Yep.
Of the two, then which the highest one is the base peak?
So the base peak is just simply the largest, meaning tallest peak in your spectrum, so it's always going to be that propane one that's tallest. Base peak is just in reference to the peak that's most abundant.
Why the propane has the base peak in this case? Is there any particular reason that make it has that high magnitude there?
That's a good question, and it factors in a couple of things. Your most abundant peak is oftentimes due to either A, that cation being the most stable potential cation that can form after fragmentation, or B, statistically it's the most likely one to form. So in this case, this is more a matter of statistics because they're all primary carbocations. So your chance of hitting 1,000 of these pentane molecules and obliterating them, your statistical probability of finding a propane cation is the most likely because it's kind of cut roughly in the middle. Does that make sense?
Is that carbon cation in the middle position? I mean, it's always the third one, whether we're from left or right.
Yeah, it's usually due to carbocation stability, but whenever there's a tie, it's statistical probability. I'm not going to stress that too much. I just want us to be able to identify the fragment peaks as much as possible.
So why do you have two large peaks in the second group? Like what's over here for you?
That's a good question. Oftentimes you get a cluster. So in this case, ethane should be what? That should be C2H5. So that should be 24 plus 5. That should be 29, which is right here. Question is, why are we observing something that's -2 a lot? What's probably happening is when you lop off 2 hydrogens off of each end, they can actually form an alkene or something like that, or at least something that's resonance stabilized. I'd have to look into that in more detail, though. That's a good question, and I'll try to get back to you.
So which one is N+1?
That's a good question. So if we look at our parent ion, like I said over here, we've got this little itty-bitty guy right next door to it. This is our parent +1 peak. And this parent +1 peak doesn't look very interesting, but it provides us a huge amount of information regarding the molecule. And so we're going to cover that tomorrow. But the isotopic abundance gives us clues to how many carbons are present in our molecule. So if I give you an unknown sample, you can actually look at the parent +1 and roughly deduce how many carbons are in your unknown sample. So I think that's where we're going to stop today. Tomorrow when we come in, we're going to do a lot more thorough analysis on that M+1 peak and even the M+2 peak.